Okay, this is a recording of May 2020 Unit 1 exam from Edexcel International A-Level. I did the multiple choice a while back and I didn't have time to do the Section B questions, so I'm going to go through it on this PDF version, and just to give you a look at the solutions that I've written out so you know how to lay out your questions in a clearly communicated fashion. So I won't be spending that much time explaining it. You can just look at the answers and try to work out how you've done it wrong, how you could improve, etc. I will occasionally explain things. I'll use a highlighter pen to clarify any specific points. Okay, so question 11, it says every litre of fuel used in a car engine releases 32 megajoules of energy. So remember the mega. Some students still struggle to remember what megajoules means, so I've written it up here in standard form for you. During one journey, the car uses 65 litres of fuel. So you know how many litres and you know how much each litre releases. The car journey lasted 8 hours. So remember that when you're working out things, you need to convert time into seconds. And it wants you to show, that means mathematically, that the average power over that time, the average power input to the engine was about 70 kilowatts. So you use power equals energy over time. You change the megajoules into standard form, divided by the 8 hours in seconds, and you'll come out with 72.2 kilowatts, or 72.2 standard form 10 to the 3 watts. So that's how you do the first bit. Second part B, the car traveled a total distance of 730 kilometers. So again, you have to change the units to meters during this journey. The average force of the engine was 2.1 kilonewtons. So once again, you've got to make sure you don't make a basic error of not changing the units to standard form. Show that the average power output, so before we worked out the average power input from the fuel, now we're doing the average power output based on the information given. So we know the average force is 2.1 kilonewtons, and if we know the average force and we know that the distance was 730 kilometers, force times distance over time taken, you'd be able to work it out. So force is 2.1 times 10 to the 3 from here. 730 kilometers in standard form has been converted from the information given, and you divide it by the time, which is again 8 hours. So 8 hours, same as above. So it's the same time as before. And therefore you work out that the power output was approximately 50 kilowatts. It comes out to 53.2 times 10 to the 3, which is kilowatts. Then they simply want you to work out the efficiency, and efficiency can be power output over power input. Efficiency can just be a fraction, or in this case, out of 1, you divide those two numbers, you get 0.74. Doesn't ask for percentage efficiency. If it did, you just multiply that by 100 and it will be 74%. Okay, the next question shows a person riding a unicycle. The unicycle moves at a constant speed. So if it's telling you it's moving at a constant speed, it means the forces are balanced in the horizontal direction. The vertical forces, R and W, act as shown. Okay? So, looking at R and W, it wants you to say the magnitude of each force is represented by the length of the arrow on the photograph. Okay? Assess whether R and W, the forces, are a Newton's third law pair of forces. Remember, Newton's third law, you need to make sure they're testing to see if you know what Newton's third law is all about. Okay? Well, it's quite simple. They're not. Okay? So R and W are different types of force. One is a weight, which is due to gravitation, and one is a reaction, which is due to a contact. Okay? So therefore they can't be the same type of force, and if they're not the same type of force, then they can't be Newton's third law pair of forces. So they are not Newton's third pair of forces, because they must be the same type of force acting also on different objects. Now, so they aren't acting on different objects, they're both acting on the same object. So, and the clarification here is that weight, of the rider, while R is a contact reaction. Okay, so that shows that it's a different type of force. Those are the three ways to get the marks, the 3 marks you need to get. Okay, then it says explain the motion of the unicycle. Your answer should make reference to all of the forces acting on the unicycle. Well, motion is in 2 perpendicular directions, vertical motion, and horizontal motion. So it's 2 marks, so presumably that's what they want you to do. Vertically, the resultant force is 0, so there will be 0 acceleration vertically. No change in vertical motion or height. So if you look back at the diagram, the W and R are equal and opposite, so they are a balanced pair of forces, but it's a Newton's first law pair of forces balance. So you have a balanced situation, so there is no resultant force, so there is no resultant acceleration. Horizontally, resultant force is also 0, as we are told it's moving at constant speed. Okay, and it's horizontal, so the direction is also forward thrust due to friction of the tires on the road, on the ground. That's how you move forward. Must balance the backward resistive forces, which could be drag and some friction. Okay, so that's horizontally and vertically. You'll get a mark for each explanation if it's as clear as I've written it. Okay. Oh, pardon me. The next question is question 13, which is about a flagpole connected by a hinge to a wall at position O. So here's the hinge. There's a weight acting downwards, obviously, and the tension in the aluminium wire connected to the wall at A at an angle. The diagram is not to scale, but it's you need to work out what the 3 forces are doing. Okay, so it says a free body force diagram for the flagpole is shown below. So here is a free body force diagram. So in other words, it's showing you the 3 forces X, Y, and Z. Well, obviously Z is acting downwards, so it's due to the weight. X is along the direction of the wire, so that's the tension, and therefore Y must be the third force, which keeps it in equilibrium. So if there are these force diagrams, it means the 3 forces together must add up to 0. And what that means in terms of vector addition, because forces are vectors, if you connect X and then add Y onto X and then add Z onto Y, it should create a balanced force situation. So the balanced force situation means you have a complete triangle. Okay? So you just need to make sure you know which of the 3 forces they are. So this is a force diagram, and you can analyze it as a vector diagram if you wish to. So basically you just drew a triangle of forces. Okay? I think that's, if you just pause the video, you can see how I've worded it for the 3 forces. So you need to be able to identify them. Okay? Part B, it says the aluminium wire will break if the tension in the wire exceeds 350 newtons. So you want to look at the tension wire, and that's 350 newtons. The wire is attached to the flagpole at B, 0.8 meters from the wall. So let's have a look at the diagram. 0.8 meters from the wall. So here is B. So this distance there is 0.8 meters. Okay, from B to O is 0.8 meters. So it looks like they're going to ask you to take moments. The wire is at an angle of 20 degrees to the flagpole. So that's given the angle that we just looked at. Assess whether the wire will break. You should use the principle of moments. So the principle of moments, they're just testing to see if you know how to take moments. Okay, so this means, and they tell you to do it about O. So taking moments about O, let's go back to the diagram. So you're taking moments about O. What does that do? It means you don't need to know the hinge force. So in this force diagram, you don't need to know anything about force Y, because it is acting through O, which is where Y is, and therefore the distance to O would be 0. So the moment due to the hinge force would be, the moment due to the hinge force would be 0. They then give the length of the flagpole. Why do you need that? Because you need to know where the weight is acting and if it's a uniform flagpole. So let's go back and have a look again. The flagpole we assume is uniform thickness, so the weight would be acting halfway along that length downwards. Okay? So once you're taking moments, and we know the mass is 15 kilograms, so if we know the mass is 15 kilograms, we can then work out the weight of the flagpole. Okay, so taking moments about O. The clockwise moment, if you look at it, is the one that's making it turn, is clockwise, is the weight. So weight times the length they're given, which is 1.2, and that's divided by 2 because it's where the center of mass would be equal to 88.29 once you work it out in Newton meters. Okay? And then if you do the anti-clockwise moments, it's t sine 20. So the anti-clockwise moment, so it's a perpendicular distance, and it's told us from before that it was 0.8 meters from O. Yeah? So the wire is attached at B, which is 0.8 meters from the wall. Okay, so when you're doing that, you need to know, well, what is the anti-clockwise moment? So you basically want the vertical component of the tension, which would be T sine of this angle. They told us this angle here is 20 degrees. So T sine 20, which is equivalent to, if you go upwards, it's the projection of this tension in the vertical direction. Okay? So that's why it's T sine 20. You're going away from the 20 degrees. So that's how I always remember that it's sine 20. So the tension is what we want to work out. We know sine 20, we know 0.8, we know everything else. You then equate the 88.29, which is the clockwise moments, with the anti-clockwise moment, and you can then determine what T is. And it comes out to 323 newtons, which is less than the braking force of 350 newtons. So the wire, you need to say this, therefore the wire will not break. Okay? Always make sure you communicate what they've asked you to communicate. Hope that makes sense. Okay, so that's a moment's question. Now a skydiver question. A skydiver jumps from an airplane and accelerates until she reaches terminal velocity. So what do you know about terminal velocity? Terminal velocity means at the point where the forces are balanced. Okay? At a time t, t1 here, she opens the parachute. So this blip must be the deceleration due to the parachute. Okay? Remember, you've done an acceleration time graph. Usually at GCSE, you would have done a velocity time graph for a parachutist, and the gradient would have been the acceleration. So, and then she opens the parachute, and a second lower terminal velocity is reached at time t2. Okay? So that's what it's telling you is happening. Explain the shape of the graph. So, how do you do that? So at time t0, the acceleration is the maximum. Yeah? At time t0 here. So when time is 0, the acceleration is a maximum and it's equal to g. Yeah? Well, the acceleration downwards, I should say, is a maximum because it's falling free fall. So you can see then the acceleration is a maximum, but gradually the air resistance will act against the motion, so the acceleration will be reduced by the air resistance trying to balance out the weight. So it says as the velocity increases, as time goes on, yeah, so after t equals 0, the air resistance increases, or the drag force increases, yeah, between t0 and between t less than t1. So from here to here, the gradient is decreasing, so the acceleration is being reduced. So the resultant force, W minus D, decreases. Okay, so at the beginning it was just W, D was 0, gradually d increases. So until it becomes 0, yeah? So you will have a terminal velocity at x on the graph. So you can see here where it becomes flat, that's where it's reached terminal velocity. And then a bit later at T1, the parachute opens. So at T1, the air resistance suddenly increases due to the parachute being activated, and the drags, it will at that point suddenly increase, and the drag will be greater than weight for that time. So remember, the weight never changes. The drag then changes with velocity, and in this case, due to the surface area of the parachute. And this would cause the skydiver to decelerate, yeah, because the resultant force is upwards against the motion of the diver, which is why on the graph the deceleration is below 0 on the y-axis. Okay? So I hope that makes sense. As the velocity increases, as the velocity decreases, air resistance will decrease until it balances the weight again. So remember, we want the drag to get back down to the weight, and that y on the graph, yeah, it reaches a new terminal velocity. Okay, and that's how you slow down. So this is a good analysis for you with a parachutist. Normally they give you velocity time graphs. This time they've given you an acceleration time graph. Okay, hope that helps. Question 15 is Core Practical 2. That's what CP2 stands for. It's the second core practical you need to know. A student carried out an experiment, and Core Practical 2 is to determine the viscosity of a sample of oil contained in a large measuring cylinder. Okay? A small solid sphere was released here just above the surface of the oil, and the terminal velocity V of the sphere was determined. So the whole point is using terminal velocity, and that allows you to work out the viscosity of the oil sample. So it's got 2 bands marked on there, so they're going to explain that. 2 rubber bands were placed around the cylinder as shown. When the sphere passed the top band, a timer was started. Okay, so it doesn't say how, but a timer was started. So that starts the time. The timer was stopped when the sphere passed the bottom band here. So you know the time it's traveled from there to there. You can measure the distance, so you'd be able to work out the speed, the average speed that is traveling at between there. Hopefully that it has reached terminal velocity. Okay? Explain why the top rubber band should be placed a short distance below the surface of the oil. So the surface of oil here, they place it there to allow the sphere to reach terminal velocity before you start the timer. Okay? So hopefully they place it in the right place. And it says, so you need to then explain why it's done that. So initially, the sphere will be accelerating even though it's in the fluid until the drag force balances the weight, okay, for terminal velocity to be attained. And you're hoping that will be before the first band. Okay. And then another student suggested that using an additional band, rubber band, halfway between the top and the rubber bands would help. So discuss the benefit of adding the third rubber band. Okay, well, I haven't put the mark scheme here. I'll need to double check it. I think it's because when I went through it with my class, we went through the mark scheme. So the points you need to make is if you put a third band halfway through, for example, you can work out if the time to go from, so exactly halfway, you could, for example, see if there's been a change of velocity. It will allow you to check where the terminal velocity has been reached. Okay? But we'll need to double check what they're expecting for the 2 marks there and how you differentiate it. I haven't got the time to look at it now because of the duration of this video, but I will be going through it and I will make a note in the comments if necessary. Okay, part B, the student used the following equation to determine the viscosity eta, So that's the Greek letter eta. Looks like an N, but it's curly. Yeah, it's a longer bit on the second part of the oil. So it's telling you that the weight must be equal to the upthrust plus the drag force. So the weight of the sphere must be equal to the upthrust, which is equal to the weight of fluid displaced, plus the drag force, which is due to Stokes' law. So this is the drag force due to Stokes' law. So that's just a force diagram. I think it helps to draw it. And they've given you the different letters, which stands for the density of the solid sphere, so that you need that to be able to work out the weight. So this is the density here for the weight. And then the density of the oil is also given as which is the density in this equation to be able to work out the upthrust, which, as I said, is equal to the weight of the fluid displaced, which means you need to know the volume. Okay, and then the radius of the sphere is given as r, and v is the terminal velocity of the sphere, which is in the Stokes' law drag force equation. So it wants you to identify the three terms in the equation, where I've already written it in the equation. I thought it'd be easier. You just need to transcribe them to show that this is the weight here. This is the weight, 4/3 pi, and I think this is the density of the solid. The suffix here, the small letter is difficult to read, but that's what it is. If you've got a paper copy in front of you, you'll be able to see it. And then the second one is the upthrust, which is the weight equal to the 4/3 pi r cubed, which is the volume. Both of them is the same volume. And this time it's a density of the fluid multiplied by g to change it from mass into newtons. Okay? And the third one is Stokes' law, which is the drag force. Remember, the drag force works with spherical objects only, which is the r term, the radius of the sphere. Okay, so the accepted value for the viscosity eta, just reminding you what the symbol for viscosity, used in this experiment, the accepted value is 41, and this is the units that is given to you at 24 degrees centigrade. The student obtained a value of 36. Yeah, same units, millipascal seconds. Okay. Which is less than the 41. That's what I put this here there. So the student obtained a value which is less than the accepted value. You have to suggest a possible reason for the student obtaining a lower value for the viscosity. They just want you to give a common sense answer. Yeah, so I've put the student's value may have been lower if the temperature of the oil was higher than 24 degrees centigrade. So you need to think, well, if the temperature increases, the viscosity decreases with increasing temperature. Basically, like a honey, if you heat it, it will become more runny, and more runny means less viscous. You can see the mark scheme for alternative reasons. So anything common sense, the examiner will look at your answer and see whether you deserve a mark or not. So again, you can look up the mark schemes to get a finer understanding of this question. Okay, we'll do one more question and then I'll take a break. Okay, so this one is investigating the behavior of a spring. So I actually do this with year 9 students, so they learn how to measure extension. Well, you've got to actually calculate extension. So it says this is the apparatus used. You've got a meter ruler standing in the same position each time, and you measure how much the spring moves against the meter rule. So what I tell my students is always take the meter rule reading, and from the difference in the meter rule reading before and after adding a weight, you can determine the extension by the difference between the positions. So it says a student recorded the position of the spring on the meter rule for increasing loads. So the loads, increasing loads, is the independent variable. He plotted the graph shown for loading and unloading. Loading and unloading. So this is loading and unloading as shown in the key. So this is the force and this is the extension. So normally we would put the independent variable on the horizontal axis, but you can break the rule and put the force on the y-axis. But the advantage of doing so is that F equals kx, the stiffness is then the gradient, the stiffness of the spring. And remember, that's only up to the point where the line is directly proportional. Okay? So the student continued to increase the load until the spring exceeded the elastic limit at point L. So the elastic limit at point L is beyond the proportionality limit. That means as long as you don't go past L, if you take the weight off, the force off, it will then go back to its original length. Okay? So that you need to know that K and L are different things, different terms. So K is the limit of proportionality. Up to the limit of proportionality, Hooke's law applies. Okay, so that's the bit where you want to work out the stiffness. Okay, hope that makes sense. So, explain the significance of point L. So what happens beyond L? That's what you need to write. So you need to say, if you go beyond L, it will exceed the elastic limit, which is told you in the question, and therefore, once you take the weight off, it will not return to its original length or original shape as such. So again, check the wording of the mark scheme for yourself. Remember, this is May 2020, which actually was an exam that wasn't used because of COVID. So they actually used it in October 2020, so you may find it under October 2020. The graph for loading, it says, of the spring is also shown on the axes, for unloading, I should say. I think I may have misread it. The graph for unloading is also shown on the axes. Suggest why the unloading has a different gradient to the loading graph. Well, the stiffness of the spring will be affected by the fact that you've gone beyond the elastic limit. So it'll become less stiff, I should imagine. So the stiffness will decrease if it's less steep. So you can look and see, is it less steep? Let's go back and have a look. So it looks less steep than before, so it just shows that the stiffness of the spring isn't the same as it was originally. In other words, you damaged it. Okay. A second student repeated the investigation but forgot to subtract the original length of the spring. So what will happen if he does that? So sketch on the axes below the shape of the graph that he would obtain for loading of the spring. It will be the same shape but not go through the extension. There will be an intercept on the axis. So it starts at F equals 0, but extension would not be 0 because he is basically showing the length rather than the extension because he didn't remove the original length. So it will not go directly proportionally. It will go this way. Okay? I haven't drawn it, but the wording should help you understand that. Okay. Part C has got two springs joined together. Okay? So you've got the two weights added together. Two new springs, and they're presumably identical. They're in series as shown. The springs were identical, as I assumed they were going to say, to the original one in the original investigation. Explain why the spring constants for this arrangement, the spring constant, my wording is gone, end of the day. The spring constant for this arrangement of the springs would be half, spring constant would be half for having one spring. So how you answer this question is that both springs have the same force acting through them. So both springs extend the same because they're the same stiffness. So they're feeling the same force. That's ignoring the mass of the spring, because obviously the top spring also has the weight of the bottom spring on it. So assuming the mass can be ignored compared to the masses that you've put on the slots here, then it would be true. So we're assuming that. The total extension would be double, because each one gets extended the same amount compared to a single spring. So the effective spring constant K is F over delta X would halve as it's inversely proportional to delta X. Okay? So delta X would be double the total extension. The force has been the same, so the K would be half. Okay? I hope that makes sense. So this is one of the combinations. You could have springs in series, so basically each one feels the force, and you could also be asked about springs in parallel, which in this case they would take half the force each if that was the case. Well, that's the end of this section of the paper, section B. So we'll do another video to go through questions 17 until the end of the paper. I hope that you found that useful, and I'll upload it to the YouTube channel so you can like it, share it with your friends if they're doing the same exam as you, and gradually I'll add more and more exams to the YouTube channel. So if you subscribe, you'll get notified of when the next video is ready. Okay, so please do advertise our channel, because I'm trying to get more subscribers, and if we get enough, we will continue to make helpful videos for all the units for the modular exams. Thank you very much for listening, and hopefully see you in the next video. Bye for now.